Thanks very much for everyone who's joined this afternoon. So I'll go through the agenda quickly. I'm going to talk a little bit about the challenges with AI in PCB, and these are, specific challenges in the PCB domain, but more generally in engineering. Then I'll talk a little bit about, Zuken's approach. I could generate 200 slides on this, no problem, but obviously I haven't got that many, so it's going to be a pretty compressed view of our approach. And then I'm going to talk about our first steps in AI, which is with our release that is coming out in the first quarter of next year. And I'll demo some of the functionality and you'll see some of that. And then we'll have the questions and answers at the end. So first of all, challenges with AI and PCB. So obviously, AI is everywhere these days. People use it. I'm sure many of you have used it already, particularly things like ChatGPT. Seems very clever, and you can get it to do sort of pretty creative things actually, and it's very useful in many different settings. But the problem with some of the state-of-the-art AI that exists today is this problem I've written as creativity and accuracy versus precision. It doesn't work on a slide to illustrate a chat GPT version of this, but what I've got here is a picture from something called Stable Diffusion, which is an image generator, an AI image generator. And what you can see, the prompt for this was just show me a schematic or generate me a schematic for a machine. And in this case, you can see it's generated something that looks, well, pretty reasonably like a schematic. But if you sort of zoom in on the detail, you can see, well, the text is meaningless. It doesn't mean anything. So it's given you a sort of a fairly accurate representation of what you've asked for, but the precision is not there. And similarly, you can see examples with ChatGPT where you can get very precise answers that can be wrong, so they're not very accurate. And sometimes you can get accurate answers that are not very precise. If you say how to route a PCB, it'll give you some general guidelines, but nothing in detail. So the problem is in PCB and in engineering in general, we need all three of those things to work together. We need all three of them to be, to happen at the same time. And the way this has happened before with the game playing things is, you build the precision in because the board itself controls the position of these things. But we don't even have that. We have a pretty free form sort of data type. The design can be, there's no rules that, there are rules, but I mean, there's no rules of moving or anything like that, like you would have in game playing. So the point of this is the challenge of doing this in PCB is quite different from some of the state-of-the-art AI that's out there. Another problem with PCB in particular is that just the varied number of data types. You've got text data, quite a lot of that throughout the design. Obviously, a lot of geometrical data. You've got 2.5-dimensional data as well as continuous data. So what I mean by that is, you've got a set number of discrete layers, but you can move things about in 2 dimensions pretty freely. So the mixture of those two data types causes a problem. You've also got numerical and Boolean data. You can turn on rules and off rules. You've got connectivity data and hierarchical data. And then also, not enough data. It's not a data-rich environment, PCB design, unlike something like generating images, where there's millions and millions of images you can use as a source. So all these are problems for us. And then another difficulty is the knowledge transfer. So if you're never going to design the same PCB twice. So what you need to somehow do is extract meaning or some quality of a particular design that you're using as source data, and somehow transfer that information to another design. So, unlike if you're generating an image and you pass in a load of images of boats, for example, and then you say, generate me an image of a boat. Well, that's in the source data. Obviously, it's going to be able to do that. But when you're trying to generate some information for a new PCB, that PCB has not existed before. You have to be able to create information using some quality of source data that isn't the same as what you're currently looking at. And also, you may not have even seen anything similar to it. So you have to sort of create data without having any reference to anything that you've seen before. So all these are problems, and even if, even in other engineering disciplines, something like generative engineering, creating structural shapes, the structure itself is the same material, even that is slightly simpler than what we're attempting to do with this sort of multimodal data of PCB. So these are particular challenges, and in the next section I'll go through and I'll talk about some of the approaches we've done in order to solve these problems. But that's it for the introduction section. So I'll talk a little bit about Zuken's approach to these problems and how we've solved some of these. Again, it's not every aspect of it, but hopefully enough to give you a feel for our approach. So fundamentally, our goal was always to replace our conventional automation, so standard auto routing tools, because they don't look like the results a PCB designer would generate. So right from the beginning of this, that's something we've aimed for. And we also recognize that different PCB designers have different styles, and they have different rules of thumb that they've generated or they've gathered over the years. So it's to try to incorporate some of those different styles as well into the sort of design. Another goal we wanted to perform was have this information sharing. So the AI eventually becomes a storage of PCB design knowledge, and that can be passed on to other designers. So it's a way of sort of pooling information and experience and sharing that across multiple different people. And of course, ultimately reduce the design cycle time. That's our goals for all of this. And just to sort of illustrate that a little bit, we've got a graph there which is showing, human-like outcome versus autonomy, and that's our target areas: high autonomy and a high human-like outcome. So unlike some of our existing tools and some other auto routers and things like that. And the picture at the bottom shows a typical auto route on the left-hand side versus a sort of neatly arranged routing of what you see on the right hand side. So again, hopefully that illustrates some of the differences of what we're aiming for. In terms of the PCB design process, obviously there's many areas we could tackle in this, and clearly, for whole product design, we're focused mainly on PCB part of that at the moment. And it's this area in the middle again, is where our sort of traditional tools have sat. So it's where we've focused our main, our initial target. And, so we've looked at placement, we've looked at routing and planning of the design, component breakout, that's a key thing, particularly for high pin count devices, how you get out of components. Power ground design, allocation of planes, things like that. So there's lots of different areas we've looked at in order to see what we want to focus on first. And this whole cycle of generating this and going back and, trying to reduce that rework that's necessary as part of this. But the whole thing I've summarized as, design planning. It's the whole design plan we're looking at simultaneously. So we went back to the beginning and said, well, how does a human do it? First thing they might say is, what have I done before? What can I reuse? What blocks do I have? Things like that. Can I sketch a rough layout? Firstly, is the design feasible? Do I have enough board space, enough layers, things like that? And lots of other questions. So, we really went back to sort of basics and went, okay, let's look at the whole process and how we can improve this. And again, the goal is to reduce the iteration by this right first time approach. So if you think about design planning, we looked quite a lot at the hierarchical approach because we think, that's how human beings think of it. So we start looking at breaking things down into functional blocks, looking to see what, main interconnects are between these blocks, the density of those channels are, things like that, what the restrictions are for those things, how, and then when you think about this plan, of course, you're also thinking, how do those blocks fit together? Does the placement need to be different in order to optimize it in some way? So there's a lot of it is, just looking at the design from a higher level to start with. And then, once you've got that, you can start to think about more detailed plans and breaking the design down into more and more detail as you go down. And to illustrate that another way, so if you start with just a PCB, and then you can break that down into functional blocks at a lower level, and then maybe break those down into component groups depending on functionality, and then break those down into components. I've called it components, but really I mean components, routing, just different smaller and smaller areas of the design. And what we've done is come up with a method of describing this. So this is, we got the interconnections between these blocks, as well as how the blocks themselves are arranged and routed. But in terms of description of this, what we've got is something we've called functionality level. And this is a method of describing characteristics of these blocks. So functionality level 0 is the PCB level. Functionality level 1 might be a functional block. Component level, or sorry, groups of components there might be functionality level 2, and that might also include things like bus technology, DDR4 or something like that. So that's functionality level 2. And then functionality level 3 is this sort of detailed routing. Can I route under this component? Does it generate heat? Should I put tracks under it? Sort of more detailed questions. So this functionality level 0 to 3 is information that's passed throughout, along with the AI, throughout the design process, and is used to control many aspects of the planning process, as well as more of the detailed routing and placement. This information is passed through the entire system. And so another way to think of that is just representing it a different way. Again, if you have a design like this, then this is the functionality level 0, and there may be things in this board like, this isn't, but for example, if you said this is a military board, or this is some critical board that is going to be used in a harsh environment, you might not want stacked vias or something because they're unreliable in that environment. So again, the whole point of this is, if the AI recognizes that description of the board is similar to others it's seen, and you've never used stacked vias in those, so it knows, okay, well, I won't use stacked vias because you've told me this board is similar to what I've seen before. I'm not going to reuse that technology because that's what I've learned from looking at the data that you've already given me. And then functionality level 1, you might break that down into blocks like this. And again, that information about, for example, being military application or something can be kept throughout all of this. But then there are more rules and more, sort of rules of thumb that come in based on the technologies identified in the blocks. And as you work your way down the design, so then, you go, well, this CPU memory block, there's some characteristics of that. And then further down, well, actually, now I can recognize this is an address bus. It's got a branch topology. You might identify the actual technology of it, and that's functionality level 2. And then you keep going, functionality level 3. Right now, I can get some information about the detailed routing. And if you change the application for the PCB, I don't know why you would do that, but if you do, then obviously that has implications all the way down that hierarchy and changes fundamentally the decisions that are made at different levels. So again, that's the functionality levels, and this is how the information is passed between designs, and also from designs you've looked at for training, and then applying to new designs. It's using that same information all the way through, and it's a way of extracting characteristics and knowing, you probably want me to reuse those characteristics. Another example is, there's at the top of the screen, there's obviously some memory devices there, and you can just obviously route through the via field. You might not want to do that in some instances, but it knows if it's memory and you've got multiple chips in a line and you're on this particular technology, you probably want me to route through the via field. So again, it's trying to get information about the design decisions that are made based on these functionality levels. And it has to take that from source data and then work out how to recreate that and how to apply it to new designs. And also, one of the things we've done is given the AI complete access to the existing tool set. So there's new AI tools in there that can put tracks in directly, but also they have an awareness of the existing tool set, interactive tools that the AI can drive, and then even auto routing tools, auto placement tools. So the AI actually has complete access to the full tool set in order to do that. And that's one of the ways, from the first section of my presentation, that's one of the ways of helping with this precision is by using the existing tool set. It knows about the rules. Well, the AI can be the creative part and get the accurate sort of plan of what it needs to do. And then the existing tool set can handle some of the precision. So again, that's a very quick overview of some of the technology that's involved in there, sort of PCB focused rather than AI focused, but I hope that makes sense to everybody. So now I'm just going to talk about the first steps we've made, and hopefully some of this will make sense in the context of some of the approaches I've talked about before. And this is our first release next year. So I'll show some of the functionality that's in there. First of all, just a little mention of the architecture. We chose this deliberately because of one of our goals of sharing knowledge. And this is basically the AI is sat on a server, and it can actually be the local machine. It doesn't need to be a separate server, but this is where we see a lot of the advantages. And you can train these things called brain files. When I'll talk about the roadmap in a minute, and this will make more sense. But so you can train these things called brain files, which take knowledge from existing designs, and then they get stored on the server. And once they're on there, then they can be used by other people, and that sort of knowledge, if you like, of PCB designing can be transferred from one version of Designforce to another, or from one PCB design engineer to another PCB design engineer. So that's sort of a fundamental point of our architecture to do that, to enable the sharing. I'll start with a small one. This is something, we always had the goal when we were generating this functionality that if some side sort of technology came out while we were working on it, then we would release that as a separate tool as well. So this is one of those examples. Came out of the requirement for planning, which is getting out of pin fields or sets of wires in the right way, and it looks at two ends of a set of tracks at the same time to work out what's the best way to mesh these together. And actually what it can do is generate many dozens of these solutions in a few seconds, and then presents those. The user can look at those and can choose through them. But this is all really part of the design planning process, so it was some side effect of that. And this is just showing some of the functionality. So in Designforce, again, the server is running in the background at this time, and Designforce is constantly in communication with it, and you can just say, well, I want you to search end solutions. So then the AI is saying, okay, well, I'm quickly generate a load of solutions for you. And in this instance, you can just cycle through them and you can see the different results, and you can pick one you want and you can just lay it down and then it's fine, it's done. Slightly different example. So the solutions are cached as well within the applications. So once you've generated one there, you can see there's one already there. I, in this case, want to place a track through these pins and it won't fit. So I can just say, okay, well, go back to this and say, right, show me some of the other solutions you had, and you can just cycle through them until you get one where you go, okay, right, fine. Now I've managed to create a gap there. Thank you very much. Now I can put that track in now where I wanted to put it. So again, it's just an easy way of just quickly cycling through the order of these connections in order to do that. But the ultimate goal of this is to take some information about style from the user and be able to generate track patterns that are similar to what it's seen before. So moving on to another piece of functionality, which is really one of the main overarching pieces of functionality for this whole development, which is Smart Order Route. What this does is if you can select one connection in the design and it sends the whole design to the server. So always the whole design is sent to the server, because the server is interested in what is the design plan. That's what the server is trying to do, is generating a plan of the whole design. And even if you've just asked it to do one connection, it will still generate the whole design plan and then but send you back just the bit that it's interested in, because obviously it needs to reserve space for other tracks that are going to go in later. So it's keeping that in mind, even if you're only asking it to do a small section of the design. And just as a very quick video, just to show it in operation. You can do whole board, or you can do just parts of it. Eventually, there's different brains that you can select in there. There are two settings in there at the moment, but eventually there'll be user brains and things in there that you can train yourself, and you can see it's done. So it's just basically, it's pretty simple design just to show what happens, but it's very quick, and it's done the whole design plan there. And just some example pictures, just so you can see a sort of a close-up routing. And what I'm trying to show with this is hopefully that it's not like a sort of traditional auto router. It's considering groups of connections and how to keep them together, similar functionality of connections, how to just basically make it look more like a human has routed this. And our final piece of functionality in the next release is something called the Mimic Router. This is a two-stage tool. So you do a scan of the design, and what it is looking for is areas of the design that are the same or similar. So groups of components that are similar. And once it's found those, then one of the things you can do is you can say, right, okay, I want you to copy what you've seen in that area. Now, again, thinking about our original goal, of one of the questions I was mentioned at the beginning was, can I reuse parts of design? And you can see how this technology fits into that. Now, at the moment, it's just on a single design, but of course, if you're starting to work on new designs, this is a way of storing existing technology and saying, right, I can reuse this. Now, in this video, you can see that I'm just putting some tracks in, and it's modifying the tracks based on, what obstacles there are in the sort of destination, if you like, and I can route on either of them, and you can see in that example there, it's chosen a completely different pin because it's worked out, well, those pins are equivalent. It's not exactly the same layout. So this is not like a copy and paste type operation. It's more adaptive than that. The AI is trying to understand what is the intention of the routing, how, what was the designer intending when they were putting these tracks in. Probably a better example is this, if I run this one. So this is batch mode. This is, in this case, I've got two similar copies, obviously, but they're not exactly the same. I've also put some routing on the destination one on the right-hand side there, just to make it a bit more difficult. And then basically I've said, okay, you've recognized these patterns, just copy it across. It tells you how well it did. And you can see there from the pattern that, it's modified the tracks around what was already there. It's also shortened that diff pair, because the component's been moved over because there's a slot cut in the board, so it's not in exactly the same place. You can see the track at the bottom as well. It's decided, okay, well, you went straight up, but I can't go straight up because the positions are different. So again, it's trying to adapt known sort of, routing patterns in a non-identical way. So it will adapt as much as possible in order to achieve what it thinks is the goal of the designer. So that's the sort of three main tools we're releasing in the next product. But just to talk a little bit about, some of the benefits of Smart Auto Router in particular, which was the middle one. Again, this is just comparing our traditional auto router with the sort of basic brain functionality. I'll talk about what that means in a minute. Hopefully you can see from the pictures that the one on the left is, looks like auto routing, and the one on the right looks, different, looks a bit more human-like in the way it's routed. But again, if you look at the numbers, you're talking, because of this hierarchical approach, which is a much better way of approaching the design process. You're talking about auto router. Sorry, this was averaged over, I think, nearly 9 or 10 designs. So if you look at the auto router, average their routing time for these designs was 2 hours and 8 minutes. Smart auto router average was 8 minutes and 58 seconds, and it had a higher completion. So this fundamentally illustrates that the approach we're taking with this new method is far better than a traditional sort of auto routing way of doing it. The other advantage is, of course, because the tracks are laid out in the way they are, if it doesn't complete, then you can see much more clearly what the result is, and you can see what you need to finish off. Whereas with an auto router, it's much more messy. It's much more difficult to see what bits are missing and how you need to move things around and things like that. So that's another advantage of this type of approach. So I'll just talk a little bit about some of the roadmap things for the next release. What we are releasing is basically point 1 and point 2 on that slide. So it's the autonomous intelligent place and route product, which is the base product for the whole family of AI functionality. And then the basic brain, which is effectively Zuken's trained AI. Then in the future, dynamic brain is then customer trained AI. So this is when you can take your own designs and you can feed them in and say, this is how I want you to do some design. I want to place it like this, I want to route it like this. So that's the future thing. That's really where the strength of this comes from. And then the autonomous brain is more sort of self-learning. So it then will do exploration of the design and itself and try things out and measure how good it thinks it did. So one way to think of this is number 2 is Zuken trained, number 3 is customer trained, number 4 is AI trained. So it's AI, teaching itself how to do some of these things. And that's where the interesting stuff starts happening at that level. So that's it from me. That's a very quick sort of overview of some of the work we've done in Zuken. Just to summarize the 3 sections, really, AI in PCB design is a new challenge, and it's even got some differences to other engineering disciplines. So it's a tricky new challenge, but it's very interesting. Zuken itself, we're having to push the boundaries quite a lot of current research in order to achieve some of the things we're doing. And our approach, I think, is unique. I've got a reasonable awareness of what other people are doing, and our approach is quite unique. Just trying to do this human style approach to things is sort of biting off a big chunk rather than trying to tackle something smaller. And yeah, our first release coming soon is coming next year, beginning of next year. So that's it from me.